Welcome back. Okay, so last time we talked about the first derivative, which describes direction, but now we're going to talk about the second derivative, and the second derivative actually describes concavity. Well, what is concavity? Concavity is just kind of the direction that a function is curving up or down. So if I have kind of a, I don't know if I want to say like a function, a pattern that looks like this is called concave up. And here, this would be called concave down, all right? Concave down, so if it's concave up, it's kind of like a cup facing up. If it's concave down, it's like a cup facing down, I guess. And where we change direction is what's called an inflection point. So that's an inflection point, or you might see it as a point of inflection. A point of inflection, or even sometimes like a POI, or sometimes even just POI, poi, like a little, I don't know, it makes me think of a fish, I don't know why, but anyway, so concavity of a curve can change, and when it changes, that's our inflection points, our points of inflection. So let's actually kind of test for concavity here using the second derivative. We're going to use the second derivative to find out where our graph is concave up and concave down. So we are given that f of x is equal to 1/3 x cubed minus x, and we're asked to determine the open intervals on which the graph is concave upward or downward. This test is very similar to the first derivative test, except that now we're using the second derivative. So first we'll find our first derivative. So f prime of x is equal to, looks like x squared minus 1. And if we solve that and set that equal to 0, then x would be equal to plus or minus 1. And these are our critical numbers. You remember? These are our critical numbers. And we could find out where it's increasing and decreasing if we wanted to, but I'm a little more interested in our concavity today, so we're going to find our second derivative. Well, our second derivative of x is just going to be equal to 2x. And then we set that equal to 0, and x is equal to 0. And this is our critical number of f double prime of x, critical number of f double prime of x. And now we're going to use that critical number to test just like we have before. So I kind of draw that sort of number line, and I've got 0, and I'm going to test, I guess we can test -1, and we can test +1. Well, -1, so f double prime of -1 is equal to -2, so that's going to be concave down. And f double prime of 1 is equal to 2, which is positive, so that's going to be concave up. All right, so our graph, I kind of didn't leave myself a lot of space here, but our graph is concave down from -infinity to 0, and concave up from 0 to infinity. All right, pretty basic stuff. And you could actually do the first derivative test here if you wanted to and find out where we're increasing and decreasing, but I'm just really interested in the second derivative today because I think you already know how to do the first derivative test. So let's do another one here. We're asked to determine any points of inflection and discuss concavity. I wrote discuss instead of discuss. Concavity of the graph of f of x equals x to the 4th minus 4x cubed. Okay, so let's do that. Let's actually discuss this. It's kind of something interesting to do. Well, first we want to find our points of inflection. All right, we're going to find f prime of x is equal to 4x cubed minus 12x squared. And if we wanted to, we could set this equal to 0. Factor out of 4x squared, we'd be left with x minus 3 equals 0. So it looks like x equals 0 and x equals 3. Those would be the points that we would use for testing for our first derivative test, right? Well, then we need to find our second derivative. So f double prime of x is going to be equal to 12x squared minus 24. So I can factor to 12. I'm left with x squared minus 2. I set this equal to 0. So, no, not x squared. X? Ooh, you know what I forgot here? An x. Woo! That's bad. Take that out. There we go. This is better. x minus 2. So now I have x could be equal to 0 or x could be equal to 2. Okay? And now I'm going to test this. I'll do it right here. So I've got 0, I've got 2. So these are, well, we'll find out if we have a point of inflection, right? So we're going to test, let's test -1, 1, and 3. Okay? So f double prime of -1 is equal to, that's going to be positive, so we're going to have what? 12 minus a negative, well, plus 24. Ugh, I'm so lazy, I'm just going to do it in the calculator again. Why do I do this? It's not very good teaching, but honestly, so 12 times -1 squared minus 24 times -1, I get a positive 12. So I thought that's what it was. Anyway, so that's concave up. Okay. Then if I put in 1, oops, I put in 1, delete that, delete that. F double prime of 1 is equal to -12. Can you see my calculator here? I think so. And if I put in 3, so if it's -12, that's concave down. If I put in 3, we get 36, so that's positive, so that's concave up. Okay, so our graph, f of x, is concave up from -infinity to 0, and then again from 2 to infinity, and concave down from 0 to 2. And we have a point of inflection at x equals 0 and x equals 2, because our point of inflection is just where we change direction, right, in our graph? So that's it. Second derivative test, basically just as simple as the first derivative test, just that you're finding different information. And we'll use this to do curve sketching coming up. But if you have any questions, leave them in the comments, and I'll see you in class. Bye!